Right, greetings to everybody. I hope you can hear and welcome to the Signpost to 4DWC event this evening. I'm Dorrik Stow. I'm going to be your host for this evening. And the last time I looked, there were up to nearly 200 people who had registered for the meeting. So we're still waiting for a few more people to trickle in. But let me take 5 minutes more to just introduce the evening to you. First of all, our thanks, many thanks to SEDS Online for allowing us to have this meeting through their auspices. So a great service they're doing, and many thanks to them. Thanks also right at the outset to Tom Dodd from British Geological Survey in Edinburgh, who has organised this Signpost to 4DWC event. As many of you will know, this is lining up to be the 4th deep water circulation conference that there's been. We held the first one in Bayona in Spain, organised by Javier Hernández-Molina and colleagues in 2011. The second one 3 years later in Ghent in Belgium, organised by David van Ruij and colleagues. And the third in Wuhan in China, organised by Professor Xinong Xie and colleagues. And the fourth, this one was due to be held very early in 2021. We postponed it for a little bit due to COVID and now have postponed it until September 2022. And we fully hope that you will be able to visit this beautiful city of Edinburgh that you see on your screen there, and also participate in the fantastic field trip to carbonate contourites on Cyprus after the main meeting, and also to various local features of interest, both historical and geological. So that's all lined up for September 2022. But we didn't want to leave everybody hanging with a postponed conference alone. And so we have organised this, or Tom has organised this Signpost to Edinburgh virtual conference, small virtual meeting this evening. And in a minute, I'll pass over to Rachel for chairing that. We've also busy organising or arranging 2 further conferences, Contourite related meetings next year, and Javier will introduce those a little bit later in the programme. And we've nearly completed a virtual special issue of marine geology, which will have many of the items and talks presented as papers and many more than that. And that is going to be introduced by Ujdin a little bit later in the programme as well. So today we have just five short talks, as you see on the screen, by Elda, Henriette, Javier, Mike, and myself, on a range of current topical items within the contourite bottom current realm. Each of the talks will be about 25 minutes, with 5 minutes of pertinent questions immediately after each talk. We'll have then 15 minutes of updates on the special issue and on future conferences following that, and then a formal, we say formal, an open forum discussion that I'll chair after that, where we'd like to pick up as many of the questions that you didn't ask during the talks, but also generate as much discussion on any relevant topic within the contourite family of activity. And as ever in these events, both for Rachel as she's chairing the meeting and for myself in chairing the open forum afterwards, either raise your hands or preferably even type into the chat session, and we can pick up your talks, your questions at that point, either asking you to ask them, or we'll ask them on your behalf. There will be, following the whole meeting, if you're still around and if you've gone to get yourself a pint of beer or a glass of wine or a cup of coffee, depending where in the world you are and what time it is, there will be a chance for a much more informal social time after the formal discussion has finished. And Seds Online has agreed to leave the meeting space open for us at that point. So now, without further ado, and hoping that most of the people who are going to join have joined us, I'm going to pass over to Rachel to host and chair the series of talks. Rachel, over to you.
Super, thanks, Dorrik. Just to reiterate from a housekeeping point of view, I know we're all experts in Zoom these days, but if you do have any questions, then pop them in the chat and I'll pick them up so we can ask the presenters at the end of their talks. So if I could ask Elda, can you please share your screen while I introduce yourself? So Elda is an assistant professor in sedimentology at the Faculty of Geosciences in the University of Bremen, and also a member of MARUM, which is based in Bremen also. So our research focuses on the sedimentary processes that control seafloor morphology and sediment distribution in the deep sea. So with a particular focus on ocean currents. And she's going to talk today about some of her research in the Mozambique Channel. So Elda, I can see your screen, I can confirm. So happy for you to go ahead.
Okay, great. Thank you very much. So today I'm going to present you some of the last results that we published as part of this special issue in marine geology. And this is a study that was mainly focused in the Mozambique Channel, that is the zone between Madagascar and the African continent. And we did this study in collaboration with, it was a big project, especially between Total and IFEMER, but with the collaboration of many other research institutes, the University of Brest, the IRD from France, and also the Royal Holloway University of London, where Antoine Tiblemont was working there at the time. So I would like to start with these famous pictures where you can see the main localization of contourites around the world, and also somebody passed the mic. So where we have the main localization of contourites around the oceans. So during the last decades, there has been a strong effort done in the characterization of contourites, and nowadays we have already a good idea of how these deposits that are formed by the currents look like, and how we can identify them, mainly based on seismic data, but also in sediment cores, which are the typical sediment facies from contourite deposits. But actually, we know much less about the processes that form these contourites. So we have some ideas, some conceptual models about how bottom currents flowing along slope can generate this type of deposits, and also some other processes such as eddies or internal waves that can also affect the seafloor. But there are very few measurements of the deep sea, especially near the seafloor, because it's difficult to get there, and it's very expensive to do this monitoring near the seabed. And most of the studies of oceanography are mainly done in the upper part of the water column. And also, apart from that, there are also not so many studies of experiments, in flume tank experiments, but also numerical modeling of the interaction between ocean currents and the seafloor. And that's what motivated our study. And we focus on our study in the Mozambique Channel. So we are in this area where you can see here the surface currents that are obtained from, in this case, also a model. And you can see here some currents that are coming from the north of Madagascar, and then large eddies that form in the Mozambique Channel and move southwards, and then they are incorporated and become part of the Agujas current system. So this is an area that is strongly affected by very intense ocean circulation. And that's why we also wanted to go there. And apart from that, we have as well a good idea from previous studies about the distribution of contourites in the margin. There were already some regional studies that located the main contouritic deposits and erosional surfaces in this area. And we also have some measurements available near the seafloor and numerical models that were already calibrated or checked with these measurements, so that they were working nicely and they were matching the measurements in most part of the basin. Of course, we don't have measurements everywhere, but we have some measurements inside the channel and also from other studies along the Mozambique slope. So the approach of this study consisted in mapping most of the contouritic features that we could find in the area, using multi-beam bathymetry at different resolutions. So in the upper part of the slope, we have up to already 5 meters, but farther in the deep part of the basin, we go to 40 meters. But we also use seismic reflection data, so bottom profilers and sediment cores. You see here the location of the main seismic data that we have on multi-beam bathymetry, and we compare this with the bottom currents that were obtained from a numerical model. That is a ROMS model in the Croco version, and this was calculated during 21 years. And the resolution of this model is around 2.6 kilometers, so we can resolve the large contouritic deposit, not the small bed forms. So as part of this study, we also suggested a simplified classification of contourites that will allow us also to compare the bottom currents with the different types of deposit or contouritic features. So we separated that in 3 groups. The first group will be the features that are dominated by deposition, that means the contourite drifts, and we have identified 4 main types of drifts, or actually 2 demanded drifts that can be either parallel to the slope, so we have the separate mounted drifts in this case, or they can get detached from the slope, and we have the detached mounted drifts. We can have the plaster drifts, mainly on slopes with this typical convex shape morphology, and there are many areas of this zone that are covered by large fields of sediment waves. Then when the currents are a bit stronger and there is more winnowing, then we have the formation of sandy contourites. It's deposits mainly dominated by sand. So we can find them on contourite terraces that are flat surfaces that are found on the top of plaster drifts. We can find also sandbanks that are often on the top of seamounts, or sandy condensation layers that we can find in different environments. And then very often we can find also sand dunes that are related either to sandbanks or also on contourite terraces. And then if the currents are even stronger, we have erosional features that can be also different types. So either a moat or a contourite channel when we have more truncations here, and these are related to the separated mounted drifts. Or we can have contourite terraces that sometimes have also some erosional features. And can have channels, furrows, scours, and even larger zones of erosion abraded, named as abraded surfaces. So what we did is we compared the local, well, we had the map with the distribution of all these features, and then we compared this, we analyzed what's the typical values of bottom currents in these different environments. So we compared that with the mean speed. You can see here also maximum speed near the seabed, and the mean eddy kinetic energy that shows what's the variability of the currents. So if we start now with the places where we have the strongest currents, these are the abraded surfaces. We can find them on the slope here. So we have some areas with dominated by truncation, so with a strong erosion. But we also have other areas that is the whole seafloor that is completely abraded. You can see here some truncations at the seafloor, and these zones can extend over hundreds of kilometers and affect larger surfaces. Then other areas of strong energy are the moats. you can see here an example that is at the foot of the slope of the Mozambique margin, and it has a mounted drift associated with it. And we also have moats that are related to seamounts, and even small, also between small volcanic edifices that are in the central part of the margin. You can see them also here in the bathymetry, all in between these topographic highs, we can see these moats and these drifts that are associated with them. So in this area, when we have a look at our model results, we find here the highest values for abraded surfaces and moats in the mean speed that can be around 10 centimeters per second, and maximum speeds in these areas can be over 40 centimeters per second, which are values typically that can erode the seafloor. But we also see a strong variability in these environments. And the mounted drifts that are the deposits related to these incisions, to these moats, we have already lower values. So we have already mean currents that are below 8 centimeters per second typically. So when we have a look more in detail at one of these modes and separate mounted drifts, and we have them here is the mean speed at the location of the profile, you can see the bottom current that is flowing at the base of the slope, northwards in this case, and is flowing along the moat. And then we have the formation of the drift that is in the adjacent zone with the weakest current. So in this zone, the currents are strong, weak enough so that a deposition can happen. So we have the accumulation of sediment in this zone, and we have the formation of this mounted drift. So we have a decrease of energy that is maximum at the moat, and then farther offshore it decreases to a minimum point. In the areas where we have a bit weaker currents, but still strong enough to create winnowing, we can find sandy condensation layers, that these are zones where we have accumulation. In this case is pelagic sediment, so it's mainly just foraminifera that are getting accumulated. So all the fine material is being transported away and just the forams are being accumulated. And we found that in some topographic highs that are at the base of the Mozambican slope. And in this area, the currents are also quite strong along these topographic highs. So we have erosion on one side, and on the other side, we have this strong winnowing that just accumulates tens of meters of this contouritic sand. And we found the same deposit or very similar deposits also along the flanks of the Zambesi Channel. So here we have the Zambesi Valley as a turbidite system, but this is also affected by bottom currents or their flanks. And we have two cores on this area, and we found also very low sedimentation rates and these typical contouritic sands with high accumulation of foraminifera. Most of the Mozambican slope is composed of a series of contourite terraces and plaster drifts at different levels. So here you have two examples of the ones that are in the upper slope. And you can see here that they have a convex shape of morphology with a relatively flat upper surface. That is the contourite terrace. And they extend a long slope for hundreds, thousands of kilometers, and they can be also relatively large. And we have some cores also in this area, and the plaster drift is relatively muddy, and when we move towards the contourite terrace, we have the accumulation often of sand. And when we have a look at the bottom currents in these deposits, so in the contourite terraces and in the plaster drifts, actually we have average currents that are more or less the same as in the mounted drifts, both on the contourite terrace and in the plaster drifts, and also the same for the maximum speed. We are maybe even a bit higher than in the mounted drifts because we have here some areas where we find these plastered drifts and contourite terraces where the velocity is sometimes in some areas quite high, and also with an average eddy kinetic energy. So we don't see any major differences between the contourite terrace and the plastered drift at this scale and at this resolution. And that was a bit surprising because actually we have many evidence that on the terrace there is erosion and this coarser material, so the energy is expected to be higher. So we were expecting to have a stronger bottom currents than in the plastered drift. So we see in the one, for example, the terrace here on the upper slope in front of the Zambesi Delta, that we have a large channel, and we see erosional surfaces, truncations are in the zone related to this channel. And also we can find zones with sand dunes, and we see also erosional surface below these fields of dunes that indicates that we have a stronger energy in this area and then kind of decreasing upslope, and these dunes are migrating upslope. So these dunes are relatively large, so they can be up to 150 meters and, of wavelength and height of around maximum 1.5 meters. But the question is then if bottom currents related to the main circulation are not very different on the terrace and on the plastered drift according to our numerical model, what could be then the other process that could affect these zones? And on the seismic, we also image internal waves that are related to the pycnocline in the upper slope. So with this, we can explain maybe what is going on in the upper slope, but maybe in the deeper parts where we don't have such a strong change in density in between the different water masses, maybe the processes are different. But in the upper slope, where we do have a strong contrast of density, we could observe internal waves that were moving towards the upper part of the slope. You can see them even a bit better here. And when they break on the slope, they create more turbulence and increase bottom currents at this area. And this will explain also why these dunes are probably migrating upslope. So we think that internal waves could have also a strong impact on the erosion of these contourite terraces. And then another very important feature of the Mozambique Channel are sediment waves. So most of the basin floor is covered by sediment waves, and they are very large, so they can be up to 3.5 kilometers of wavelength, and heights that can be up to 75 meters. You can see some examples here. Some of them are mainly aggrading with weak migration. In the southern part of the basin, some of them have more migration, and the orientation is very variable. They can cross each other, is kind of chaotic actually. And in some areas, we also see furrows with more dominated by erosion, and they have also different orientations. So some examples here, some more there, and then they can even cross or form almost in the same place as the sediment waves. So the sediment waves form generally in areas with relatively weak bottom currents that are more or less similar to the bottom currents where we find the mounted drift. So that means it's in zones where we are mainly under a regime that is low enough to allow deposition, which makes sense because we see that they are mainly aggrading these sediment waves. Some of the sediment waves seem to be related also to the main current pattern. So you can see here the arrows represent the average bottom currents in this area. So they flow around this topographic high. And some of the sediment waves seem to be also oriented in the same direction. But not all of them. And actually we have these different orientations that superpose to each other. So some authors also suggested that there are these very large eddies in the area that affect the whole water column, so down to almost 4,000 meters water depths. And these eddies, of course, have different directions while they're moving, and not all of them move exactly through the same path. So this could explain why maybe some of the sediment waves have different orientations, but the sediment waves have been there for a long time. So it's also not so easy to explain how these, let's say, episodic events could generate always in one direction a sediment wave. But maybe at some point it started, and then just this initial morphology is entertained in time. And other authors suggest that maybe internal waves that are flowing at the bottom boundary layer could also initiate the formation of these sediment waves. But well, no clear answer so far. So probably we also have a combination of all these processes, and that could explain why there is such a large variety in the orientation and size of these sediment waves. In the Mozambique Channel, we don't only have pure contourite systems, but also mixed turbidite-contourite systems. So we have some examples here in the Pars Islands. So we have carbonate platforms in this area with also carbonate turbidite systems that have been affected by bottom currents. So you can see one example here with the channel levee system that is very asymmetric. One levee is much larger than the other one. And then right next to the levee, we have these furrows and evidence of erosion, and we have even a small contourite drifter next to the levee. So this system has been affected during its formation by bottom currents and generate this asymmetric deposit, but also after the formation part of these levees were eroded. And we have this also synchronous interaction of turbidity currents and bottom currents in the northern Mozambique margin. In the upper part here, so we have some submarine channels that come from the continent, and especially in the lower part of the slope, when bottom currents are interacting with the turbidity current, then this deflects the turbidity current to one side and generates these asymmetric channel levee systems that also migrate in the upstream direction of the bottom currents.
5 minutes, Elda.
So in other cases, the currents are also much stronger bottom currents and can erode submarine channels. And this is the case here of the Zambesi Valley. So it's a large turbidite system that comes from related to the Zambesi Delta mainly. And then we have the Zambesi Valley that goes down here. And you can see two examples of this system where we have a main talweg formed by turbidity currents, but then the flanks of the valley are completely eroded by bottom currents. And we have strong bottom currents flowing along the valley flanks. And we saw already before also the accumulation of contouritic sand on the valley flanks. So this is also a type of turbidite-contourite system. And all these systems in general, we have relatively weak bottom currents, especially in the zone that is in the upper part here, in the northern part of the Mozambique margin. But in the Zambesi Valley, we have relatively strong currents, well, more or less as in the other type of contourite deposits. But locally, you can see here that there are some areas along the flanks where it's especially accelerated, and these are the areas where we see the erosion. So it's not the whole system that is affected. In the main axis, we have weaker currents, but it's along the large valley flanks where we have the acceleration of the currents that you can see very well here along the channel is where we see these strong currents and also with a strong variability. So to conclude, I'd like to summarize this by saying that we have in the contour depositional systems two main scales. So we have the largest scale sedimentary features, such as the contourite drifts, the moats, or the contourite terraces that we saw in this talk. And these are in general related to the main thermohaline circulation, so to the general ocean circulation. But superimposed to that, we have other small scale features that are related to other also smaller scale processes, such as eddies or internal waves. So for example, we can have the formation, the erosion on the terrace by internal waves that can generate dunes and channels along the slope. So also to summarize, we know quite well already how to identify contourites, how they look like, and which are their main characteristics. But we still don't know much about how they are formed and which kind of processes are forming these contourites. So and what's the velocity that is necessary to form them, which is the exact process that is generating each kind of the features. So I hope with this talk also to motivate all among you to next time you go on a cruise, just also try to keep that in mind and try to measure as much as possible, because any measurement near the seafloor is precious and will bring very important information to move forward, and maybe at some point to be able to relate exactly this kind of geomorphological feature and to a specific process, and that will help us very much to advance in the paleoceanographic interpretations. And that's all from my side. Thank you very much, and looking forward to the discussion with all of you.
Yeah, thank you so much, Elda. That was fantastically interesting and beautiful data set across a very large area. That must have taken a while to work your way through. Yes. Do let me know if you have any questions in the chat, please, those are in the audience. I'll pose a question first off, though. So just wondering what role you think sort of more short-lived oceanic events might play in determining the larger scale contourite features. Do you think they have an influence, or things like internal tides or benthic storms?
Yeah, that's the main question, and that's what I cannot tell for sure so far. Because most of the large scale features seem to be quite well explained by the average current. So maybe in these cases, even if the current is not eroding continuously. So for example, when we have a look at the currents that are at the moat or on the broader surface, when we expect to have strong currents that could erode that, we have on average sometimes 10 centimeters per second. So these are currents that will be able to erode the seafloor. But it's the distribution of these bottom currents on average that is also similar to the distribution of the features, but it's not the average current that is strong enough to erode the seafloor, but it's probably the stronger events that are responsible for the long-term erosion. And yeah, it will be necessary to do more statistics on different places and to really have long-term measurements to know when the sediment is put in suspension, when we have the deposition. And in these cases, yeah, we could tell maybe for sure if this is the case or not. And yeah, so it can be that what we see on average that represents also just the strong currents that are related to episodic events, as you said, that could be just an eddy passing by. But if we have very often an eddy passing by the same area, that will generate the stronger currents, then in the long term, this is also going to create a specific current. I don't know. I think I'm turning in.
No, it's good to get. So in situ experiment would be fantastic to answer these questions.
Exactly.
Fantastic. One quick question before we move on. So from Michael, how can we distinguish abrasion surfaces from erosional truncations, apparent truncations, when the reflectors are thin or below resolution?
Well, yeah, if it is below resolution, then it's difficult to identify it. That's why I think it's always important to try to work with different kinds of resolution. So the cases I was showing of the Contourite terrace, this was visible for us because we had some bottom profilers, but on the seismic data from the industry, you couldn't see these small erosional surfaces. So it all depends, of course, on the scale. So on the seismic data from the industry, we saw these large surfaces that are eroded, but not these smaller ones.
Yeah, no, super point. Yeah, integrated data sets, so important, different resolutions. I think in the interest of time, there's lots of good questions coming, but we'll save the rest of the questions for the discussion at the end. But thank you so much, Elda.
Great, thank you.
I'm now going to welcome Henriette. You can share your screen. So we're sticking to University of Bremen. Henriette's, I'd imagine, just down the road or down the corridor from Elda right now. But we're going to the other side of the world. So Henriette's going to talk to us today about her research along the northern Argentine margin. So in general, her research combines sedimentology with fluid dynamics, good integrated work to understand the interaction of sedimentary systems with ocean currents. So I'll pass over to you, Henriette, and I can see your screen. I can confirm. You're good to go.
Yeah, thank you very much. I'm very happy to give this talk today. As you already said, it's going to be about the influence of bottom currents on morpho-sedimentary features along the northern Argentine margin. And at the northern Argentine margin, we find two elongated depressions that are classified as moats. And that's why I will also talk about the morphology and stratigraphy of moats. But before I start, I want to thank all the people that contributed to the study. So thank you very much. Let's get started. So we know that bottom currents can have a large influence on continental slope and also abyssal plains. But usually there are not a lot of current measurements near the seafloor, so this makes it very difficult to link the contourites to the currents that created them. Some authors have used CTD data to identify different water masses, here based on the salinity or the temperature or the oxygen. This can be very relevant to also understand processes that happen at the interface of different water masses, but it doesn't give us information about the speed and the current direction. So to further link contourites to oceanographic features, we need more information about the speed. For this, we went to the Argentinian margin, and something that's a bit special about the Argentinian margin is that the slope is interrupted by relatively flat surfaces that are classified as terraces. So there are 4 in the southern part of the Argentinian margin, and there are 3 in the northern part. So 3 of the terraces can be traced towards the north. They are called the La Plata Terrace and 500 meters, the Urine Terrace and 1,200 meters, and the Nicosia Terrace at 3,500 meters. And I will be focusing on the La Plata Terrace and the Urine Terrace. Both of them are located in the confluence zone from the southward flowing Brazil current and the northward flowing Malvinas current. So here you see the mean surface velocity that is averaged over 25 years. And even though this is the mean, you can see that we still have very high current speeds with 70 centimeters per second. So zooming into this confluence zone, you can see that the Malvinas current, it splits into 2 branches. And and then it detaches from the slope, it mixes with the Brazil current, and then they form the Brazil-Malvinas Confluence Zone and flow into the basin. So this was already known quite well, but what's much less known is how the velocity looks near the seafloor. So we used the same model, but now we're looking at the seafloor. And what you can see is, first of all, even though we are in the confluence zone, the main current direction is still towards the north. So it is still the Malvinas current influencing our study area on average. And you can also see that the speed is decreasing towards the north. To further understand the oceanographic setting and also the architecture of the margin, I want to show you two profiles. One that is located a little bit south of the Mar del Plata Canyon, and the other one is located towards the north. And basically you see over the La Plata terraces, this velocity is low, and also over the Uran terrace, the velocity is quite low. And over the abraded surface that is between the La Plata terrace and the Uran terrace, on average, the speed is quite high. So again, here on the picture, you see that the Malvinas current, it splits into three branches near the seafloor, and they're sort of flowing around the terrace. And here the La Plata terrace is quite wide, and when it gets getting narrower, you also see that the two branches of the Malvinas current, they are closer together. So some people are always a bit skeptical with model data, even though this model, it incorporates real measurements, and it is also tested with real measurements also near the seafloor. Still want to show you some measurements that were collected during a cruise with a vessel-mounted acoustic Doppler current profiler. And here it's displayed the velocity average between 150 and 200 meters above the seafloor. And we calculated the average speed for different areas. So first here over the Uran terrace south of the Mar del Plata Canyon, the velocity is on average 15 centimeters. It decreases towards the north, where it's only 11 centimeters per second. So this is quite similar to what we can see in the model. And also over the abraded surface, the velocity is stronger with 23 centimeters per second. Due to a lack of resolution in the model, we cannot really see what is happening above the moats. So that we can only see with the measurements. And above the moats, we can see that we have especially high velocities with 28 and 29 centimeters per second. So we want to link now the current dynamic with the grain size from surface samples in the area. So here with color code, you can see the main median grain size for near the surface, near the sea surface. White dots indicate a median grain size below 63 micrometers, where blue and dark blue dots indicate coarser material. And here in the southern area, you see more coarse material, and then towards the north, we find finer material. So we think that the northward grain size finding is due to also the decrease in current speed. You can see a similar grain size curve, how the main peak is moving towards smaller grain sizes when we look at the entire grain size curve. Over the moats, inside the moats, we can find quite coarse material, and it's not very well sorted. And also when we compare the curve from different cores inside the moat, the distribution changes quite a lot. So we further want to understand how these moats look like, and also, yeah, what current regime we have just above the moats. So in the southern moat, here labeled Uran Terrace Mode 1, it's a little bit curved, it's about 90 kilometers long. And we also see some internal terraces here, and even some small scours inside the terrace, whereas the northern moat, it's much more straight. We cannot find any internal terraces. It's about 70 kilometers long. And both of these moats, they show this typical, what's typical for a separated mounded drift, these sigmoidal reflectors. But what's untypical is they are truncated here at the sea surface. And usually they sort of thin out and become more parallel. So we thought maybe this is due to the unusual high speeds in the area, which is also reflected in the coarse material that we can find. So we projected the cores that were analyzed by Bozzano et al. In 2011 to the new collection of parasound data. And you see that inside the core, inside the moat, we have very coarse material, even gravelly rich sediment. And also at the mounded drift, we still have silty sand, whereas usually moats are more muddy. Okay, so we also wanted to understand the current dynamics. So I will show you now a profile that is just over the moat and one that is parallel to the moat above the abraded surface. So here in the ADCP data that was collected just above the moat, you can see as expected a decrease in speed from the current towards deeper water, but then just above the moat, you see higher speeds again. So the current somehow intensifies. Whereas if we look at the abraded surface, we don't see this intensification. Another profile also confirms that the intensification of the flow that is just restricted to the area above the moat. So we think that probably this current intensification is due to the existence of the moat. So what other processes, smaller processes can we have? Before I showed you a 25-year model of the bottom currents, but this also averages out some infrequent features like small eddies that are restricted to the lower part of the water column that are not always present. So for example, here the model shows that we have a cyclonic eddy just above the urine terrace. And also in the ADCP data, we can see an eddy above the urine terrace. And we think this eddy might be there because we have these diverging isopath and also slightly sloping morphology towards the north, and that can create flow instabilities in the water column, and that might lead to an eddy. Interestingly, even though on average we have quite low velocities over the terrace, we still see some truncating reflectors. So there is some patchy erosion going on. So we suggest that during energetic periods, and only during this energetic periods, the cyclonic eddies might lead to the small erosional surface on the terrace. Also inside the moat, we think we can have some very small scale processes. For example, here, just behind this little edge, we have a scour. So maybe even inside the moat, we have some very small vertices that create a scour. So we looked at the stratigraphy of more than 150 moats and separated mounded drifts, and the most common morphology and stratigraphy that we can find is displayed here on the left, where we have the reflectors. They kind of follow the morphology. They dip towards the moat and then they go up again, so they onlap on the slope side. But for example, on the Argentinian margin or also offshore in New Zealand, we also find reflectors that, yeah, they dip towards the moat, but then they onlap, they downlap at the bottom of the moat. And what Elda just showed you, or also from Javier from the Gulf of Cadiz, we have reflectors that slightly dip towards the moat, but they don't make it all the way down before they are truncated at the drift side. So if these reflectors would be completely straight, then it would be a channel, but since they are bent towards the moat, they are classified as a separated mounted drift, and this makes a moat. So I labeled them for now type A, B, and C, and concluded there are at least 3 different stratigraphic types of moats. So before I just showed you one cross-section of one moat, but what happens if we look at one moat over and over again and try to understand how the moat develops in downstream direction? So for example, here for the Argentinian margin, I'm going from upstream to downstream. We can see that here upstream, we have only a paleo mode, then it transitions more to a V-shaped mode, then to a U-shaped mode, and then just before the mode ends, it's not a mode, it transitions into being a channel. So we don't have any depositioning here, it's really a channel. So you see these truncating reflectors also in the other parts of the mode. So we can see that this mode used to be a channel, and now it's progressively infilled, but interestingly, it's infilled from the upstream direction, which is unexpected because this is actually the area where we have now higher velocities. So while I was looking through these different modes, I find it rather difficult to get a clear picture in my head how a mode looks like. And the reason for this, I think, is because if you look at the stratigraphy from seismic data or parasound data, the vertical exaggeration, that's always different. So I started to rescale the published stratigraphy of modes always to a vertical exaggeration of 16. And then I decided what type it is and what shape it is. And there are some interesting things that I didn't know before. For example, the type of mode, it seems to not be tied to the shape of mode. So you can, for example, have a type A morphology, type A stratigraphy with a U-shaped, or a type A stratigraphy with a V-shaped. Also, you can have a very large mode, here over 8 kilometers, that is a type A mode. And you can also have a type A mode that is only 2.6 kilometers. So it doesn't seem to relate, the stratigraphy doesn't seem to correspond to the shape or the size of the mode. So we also thought that maybe if you have a deeper mode, for example, here in the Gulf of Cadiz, it's at this location 190 meters deep, and it's almost 6 kilometers wide, that maybe there's a constant ratio between the depth and the width. So we measured the width between the slope and the drift, and the relief between the drift and the depth of the mode. And here you have the relief against the width, and you can see that it doesn't really correlate. So apparently you can have a very, very wide mode that has a very small relief. And so we were wondering what affects the width and relief, and also the ratio between them. One thing that is common to read, and that seems to be very important in the formation of a mode, is the Coriolis force. And the Coriolis force, the strength of the Coriolis force depends on the latitude. So we thought maybe the relief relates with relief, or the width, or the relief width ratio is somehow influenced by the Coriolis force, and thus should be somehow have a trend due to a difference in latitude. But we could not find really a trend that depends on the latitude. So we think that the Coriolis phos has apparently not a significant influence on the moat morphology. I'm not saying it has no influence, I'm just saying that other factors seem to be more important, so they overprint maybe the relatively weak influence that the Coriolis phos can have. And maybe to some of you this was expected, because the Coriolis phos is a quite weak force, so it can influence really the current dynamics on a large scale, but locally other more local processes might be more important. So we figured out that we should look at more local influences, for example, like the slope angle. So we also measured the slope angle at more than 150 modes, and plotted the relief against the slope angle, the width against the slope angle, and the relief width ratio against the slope angle. And here we finally see some sort of correlation. So apparently a higher slope angle leads to a higher relief width ratio. So we very briefly summarize this by saying the slope angle influences the bottom current, and that somehow must influence the relief width ratio. But why? So we also plotted the slope angle against the drift angle. And you can see that often when you have a higher slope angle, you also get a higher drift angle. And you also get a higher relief width ratio when you have a higher drift angle. So what we interpret is that a higher slope angle might focus and intensify the bottom current, and that intensified and focused bottom current might lead to the higher drift angle and the higher relief width ratio.
5 minutes, Henriette.
Thanks. Okay, but current cannot instantaneously adapt to a change in morphology. So you would maybe expect that there's some time needed for the current to adapt. So we looked at example here from Elda, from the Mediterranean Sea, and we measured the slope angle and also the drift angle every 200 meters. And you can see that first the slope angle increases, and then it decreases, and the mode stops to exist. The drift angle also increases, but it starts decreasing later than the slope angle. So we think that this might show that the current still needs some time to adapt to the change in morphology. Okay, to summarize this about the northern Argentine margin, we can say we see a northward grain size fining due to the decrease in current speed. We see that the current speed is lower, below 30 centimeters over the terrace, and it is higher, up to 63 centimeters per second over the abraded surface, and especially high above the moats. We also think that the sediment transport is associated with this high velocity along slope bottom current jets located here, here above the abraded surface, and here at the outer edge of the terrace. And especially this current branch might also play an important role in supplying sediment to the Mar del Plata Canyon head. About the moat morphology and stratigraphy, this is still ongoing. And so far we identified 3 different stratigraphic types of moats. We can see in the ADCP data that the current can be intensified just above the moat. And we interpret that higher slope angles focus and intensify the bottom current, and that might lead to a higher drift angle and also a higher relief width ratio. So thank you for your attention, and if you have any questions, feel free to ask me.
Super. Thank you so much, Henriette. That was fantastic. And I can't believe you've managed to find 150 moats to measure. That's a phenomenal amount of work and sifting through the literature. Fantastic. Any questions? Do pop them into the chat, please. I'll have a question to get us started. So interesting that you've got this northward finding of the sediment. Where do you think the sediment's being sourced from?
At the Argentinian margin?
Yeah.
Most of it is supposed to come from the Patagonian shelf, and it comes through the canyons, and then it's progressively transported towards the north with the current.
Excellent. So like long distance transport rather than local erosion or winnowing.
Yes.
We've got a question coming in. So have you considered as well the type of sediment that is remobilized or eroded in your moat system? So that ties into my question a little bit.
Yes, but it's very difficult to say. So we think that it could of course play a role if we have siliciclastic sediment or carbonates, because they are formed a little bit different, so that I would guess that that is important to consider, because the way it is eroded and the way it is settling down could be different, but I don't have enough measurements yet to really say for sure if that influences the stratigraphy. I think they all the carbonate modes that I've seen so far, they are sort of the most typical mode with that I labeled type A. But these are modes from the Bahamas and from the Maldives. So I'm not sure if maybe some other location you find a carbonate system with a different stratigraphic type of mode.
Yeah, no, absolutely. Again, on a similar point, so from Dorrik, he says, great talk, thank you. One question, do any of the moats show evidence of other processes, e.g. turbidite currents, and I guess also in the steeper margins, mass transport deposits?
Not sure if I completely understand the question, right? So you mean like if we can have a mass transport deposit inside the moat?
Yeah, do you see any evidence?
Well, you can, yes, I did see this. If you, of course, have an area where you have a lot of turbidites, they might destroy the moat, which is also why it's difficult to find moats at active margins sometimes. Yeah, but sometimes when you have, the downslope processes can, of course, influence the moat, and it can influence the depth of the moat. And if it's too much sediment, it can also, of course, destroy the moat. And then you can see that it's completely filled and you only have the paleo moat.
Oh, super. So one final question from Øystein. Question about the numerical models, which are fantastic, I must say, in both Elda and yourself's presentation. Do they explicitly capture temporal variability, mesoscale eddies, and sub-mesoscale vorticity? I think that the eddy you showed was influenced by the topography rather than eddy forming at the surface.
Yes, so the eddy that we see in this study, that's really just restricted to the lower part of the water column, and both in the model and also in the ADCP data, it doesn't reach the surface. So yeah, we think that these eddies really form due to the topography, but of course on the Argentine margin, there are also a lot of eddies that form near the surface, but we were not so interested in them.
Oh, super. We'll squeeze in one last little question. Mikhail is asking, are your results on the relationships between slope angle and current intensity already published? Have you published this work? Then we will all wait with bated breath to read it and cite it. Fantastic. Look forward to it. Thank you very much, Henriette. We'll move on to our next speaker. So I'll invite Javier to share his screen, but thank you, Henriette. So Javier is a professor at the Department of Earth Sciences at Royal Holloway, also leading the Drifters Research Group at the same university. So he really specializes in marine sedimentary processes, seismic, a lot of seismic. He's probably interpreted more Contourites and seismic than anybody else in the world, stratigraphy and basin analysis, core description and sedimentary structures. So we're going to have a look today with Javier at some Contourites in the ancient record, looking at Contourites and reworked turbidites in the Eocene to Miocene in Cyprus. So on you go, Javier. The floor is yours.
Okay, thank you, Rachel. So hello, everybody. My talk, as Rachel said, is going to focus more in one example from the ancient record in Cyprus, from Contourites and reworked turbidites from the Eocene to the Middle Miocene in Cyprus. So this is not really an individual work. This is a work that is an ongoing work from different institutions, and is also partially supported, economically supported by the Joint Industry Project that we are leading here at Royal Holloway. So I would like to start for the definition of a contourite. So as probably most of you know, are defined as sediment deposited or substantially reworked by the action of bottom currents. So as you know, this is a very general definition for contourites, and we are considering bottom current for those semi-permanent or permanent water massive flows with the capacity to produce erosion, transporting sediment, and finally depositing the sediment somewhere on the seafloor. So here you can see this fantastic example from Antwerp in the Mozambique Channel. Normally in the main or dominant phases association for contourite drift are these bigradational sequences defined the first time by Gontier et al. In the Wilckens. What about reworked turbidites? So if we use the definition from Stanley, so they are sandy deposits that originally derived from gravity or turbidite flows and have been partially or completely reworked by the action of bottom currents. Other authors are considering a similar definition, but they use the term bottom current reworked sands. So that means that the deposits from turbidite flow could be partially or completely eroded away and reworked by the action of bottom current. Here in this nice sketch from Stanley, you can see that the upper part is eroding away and affected by bottom currents, and could be through time being more and more eroded to produce a different kind of deposit compared to the original one. Here you can see one example from Almeria, when you can see this clear channelized body that originally were turbidites, but when you see the internal facies, the facies are different compared to the normal or the standard turbidite deposits. Or this example, when you can see this alternation of muddy and sandier deposits with these starboard ripples in this case. Not very different with this example from the Tanzania margin from Pamela Sampson. So there is so far in the literature different authors proposing a sample from these reworked turbidites and bottom current reworked sands. But all these examples, have something in common. They can be along the slope, mainly when you have major changes in the physiography of the slope because tectonic or because the occurrence of contourite terraces, or could be at the foot of the slope or the upper part of the continental rise. So apparently when you have these big changes in the morphology of the margin, you have these reworked turbidites, or they are more frequent. So are these deposit commons? So here in this compilation, you can see where bigradational sequence and bottom or reworked turbidites have been defined so far. And here in this next map, you can see the global distribution for contourites and mixed system. So yeah, bigradational sequences are very common. We had a cruise in the Gulf of Cadiz when we identify many bigradational sequences, but also we identify other facies that they don't really fit with the model for gradational sequence. That was the reason because we started to work in Cyprus. So we moved to Cyprus because by that time, we're talking about 2013, 2014, it was the most affected sample from ancient Contourites, with the main aim to understand the phases and phases association and in order to compare with offshore data that we collected in the Gulf of Cadiz and later in other areas. So here you can see the area. This is the Cyprus, and you can see the modern day morphology of the adjacent basin. And we can identify or have been defined 3 water masses mainly: surface, intermediate, and deep water masses. In general, nowadays, the 3 water masses are moving toward the northeast, and then they are deflected toward the west. This is the general circulation pattern for the 3 water masses. And this is really, in a larger scale, the water masses circulation in the Eastern Mediterranean, So this is the area. So this is the geological map for Cyprus. And we were working mainly in the Circumtrodos sedimentary cover. That are the sedimentary cover around the Trodos massive ophiolites. So mainly south of the Trodos massive ophiolites. The Contourite deposits are mainly, and the reworked turbidites are mainly in the left Cara and Pacma formation, mainly from the middle Eocene, as I said, to the middle Eocene to the middle Miocene. Okay, so obviously we were not the first working in the area. So the first one who proposed by first time the influence of bottom current in these deposits was Robertson in his paper from 1976. And then a very detailed work in the area was done by Gisela Clare and Dorrik Stow. And then since, as I said, from 2014, our group started to work in the area. It has been and still is an ongoing research, mainly from 3 countries, is UK, Spain, and Germany, from these 3 institutions and groups that you can see in the slides. Other authors, as Rolit, also propose an alternative interpretations to some of the deposits in this time or since 2014. And currently there is a German project accepted, and a new PhD degree student is going to work in the area in these deposits. So as you see, it's an ongoing research, and I'm going to present briefly the main evidence of bottom current and reworked turbidites. So we had 6 field campaigns since 2014, and in this fieldwork, we did mainly a very detailed sedimentary logs in 4 areas, and we studied the sedimentary. We did a very detailed sedimentological analysis by stratigraphy analysis, very detailed work on the microphases, mainly led by Ekuhuneke, and a very detailed ichnological analysis led by Francisco Rodriguez Tovar. We collected new data for dating in more resolution than before the different deposits, and also in collaboration with other researchers, a very detailed petrographic analysis. We also studied the mineralogical and chemical composition of the sediments, and also Link, one student from the group, tried to identify similar coebal deposits offshore. And finally, in collaboration with the Physical Oceanography Group of University of Malaga, we have done some paleocurrent reconstruction by this geological time to understand better the regional setting to explain the formation of these ancient Contourites. So I'm going to present briefly some examples from 3 areas: Petra 2 Romino, that is a key location here, Agios Nikolaos, that is around there, Corfi, around there, and Calabazo section, that is in another subbasin along the margin, okay? You see Nicolaus, Corfi are proximal section compared to the paleo margin last time, and also Petra 2 was distal. I mean, in the paleo margin was more distal compared to these other two. This is important to understand a little bit the paleography of the area by this time. Okay, so briefly, we identify different lithologies from marl, calcilutites, calcarenites, calcirrhodites, and also other facets that is really the deformation of the previous ones. And based on these facies and subfacies, we identify some facies association for pelagic and hemipelagic deposits, turbidites, mass trap deposits, bottom current deposits, and also reworked turbidites. So mainly the bottom current deposits and the reworked turbidites are using this example in the middle to late Eocene. Then they are buried by the marls deposited during the Oligocene. And then we started to have new packages with Contourites at the late Oligocene, early Miocene, and middle Miocene. And then the system was completely buried by the late Miocene deposits. So now some example of these deposits. You can see here a sample from the middle to late Eocene. It's mainly fine-grained deposits. Some of them are more turbiditic. Here you can see this example with this erosional base, this normal gradient trend, and parallel to cross-lamination. And in this case, bioturbation is mainly in the upper part of the deposits. Also, these turbidites are interstratified with fine-grained contourites. And here you can see this bigradational trend from calcilutites to calcarenites, coming back again to calcilutites. We have evidence of the action of bottom current, not because the occurrence of the bigradational sequence, but also because based on the ethnology analysis, we identified that bioturbation are from the top of the turbidite beds toward the bottom, toward the base of the beds, and also this bioturbation is through the calcilutites below the turbidite beds. And sometimes these turbidites are discontinuous or even disappear, and only you can see only pressure dissolution things related to the occurrence of these turbidite beds. But below you can see this trace fossil, this trace is infilled by the turbidite deposits. Okay, as you can see here, these are the traces, and they are infilled by turbidite deposits. And in this case, you cannot see the turbidites deposits, but you can see the infill within the traces by turbidite deposits. So that means that the turbidite deposits have been eroding away by the action of bottom current. And even in some example, you can see only the traces, not even these pressure dissolution things. So it's the only evidence that sometime in that position, a little bit up in the record, originally we had turbidites, but they have been eroding away by the bottom currents. So here you can see an example of this bigradational sequence in these muddy contourites. And you can see here in the calcilutite waxstone texture, and in the calcarenite more packstone, and then back again for this waxstone textures. Okay, so mainly the composition of these calcarenites is because the occurrence of foramens. So you can see in this big section the texture of the deposits, and they are mainly composed by the accumulation of foramens. In the quartzer seals, there is subtle wavy to horizontal lamination, but in the fine sands, you can see lenticular shapes in the layers. And the dominant paleocurrent for this Eocene deposit is toward the northeast. So in younger deposits, as I say, we have evidence of Contourites in the late Oligocene, early Miocene, and middle Miocene. But in all these three packages, the paleocurrent or the dominant paleocurrent changed to the southeast. So we had some kind of inversion in the paleocurrent affecting to this area during the mainly the late Oligocene or the latest Oligocene and the rest of the Miocene. So some example of these facies for the late Oligocene and early Miocene is mainly dominated by mass trap deposits with large slums and also turbidites, many turbidites, but occasionally you can see calcarenites with this lenticular bedding, and internally, again, they are mainly composed by the accumulation of foramen, very similar to the facet that I'm going to describe in a minute. Some example of these fantastic mass trap deposits, having Elda as an scale here, and turbidites with clear normal grading. We have also growth marks, and the composition in this turbidite is mainly by bioclast from shallow marine environment. So a little bit up in the sequence, but still in the early Miocene, we have sandy contourites. And this is the main characteristic of these deposits with parallel planar bedding or wavy to lenticular bedding with bidirectional sequence from calcilutites to calcarenites, coming back again to calcilutites, and with very characteristic banding or bedding with non-compacted layer and compacted interlayers. And here you can see this section from ECHO, when you can see that the non-compacted layer are mainly due to the accumulation of forams and the reworking of forams. And in the compacted layer, you have more evidence of very distal turbidite deposits. So here, again, another sample of deep gradational sequences for the sediment of these edges in the early Miocene, and another example of this banding in large thin sections. And here a very nice example of this, in this case, grainstone texture associated to these calcarenites. Occasionally, you can see at the top of the calcarenites, you can see cross-bedding that modify a little bit the general trend in the gradational sequences. And we interpreted this cross-bedding as sandy to the dunes. And you can see in this example that the microfacies are mainly characterized by cross laminations, all laminations, and again, different percentage in the accumulation of the forams. Also in this, in the deposit related to these edges, we can identify thicker and coarser turbidites compared to the previous and other intervals with erosional base and clearly normal grading, sometimes wavy lamination, and normally they are characterized by a truncation surface on the top of the turbidites, and above some evidence of reworking. So here you can see the base with the coarser material, and the main bioclasts again are mainly a large bioclast from shallow marine environments. Here you can see these brachiopods, red algae, or here nummulites, or these bryozoans here, of mainly shallow marine components in the turbidites. This is a sample from crinoids, or also red algae. But as I said, in the upper part, we have some evidence in these lenticular layers with bigradational trend, where there is a different accumulation of bioclasts from the base to the top. So large bentonic bioclasts are mainly in the middle part of this trend, and reed algae are mainly in the lower and in the upper part. So, and then up in the sequence, in general, in the four sections, at the top of these Contourite packages, we have again turbidites and some syndebrites before the next and last package with Contourites. And you can see here these last Contourite packages from the middle Miocene. They are thicker compared to the early Miocene, but also they are muddier. So we have a similar trend with this bigradational sequence, but in muddier deposits. And also the calcarenites, the fine sand is again because the accumulation of forams mainly. And you can see here another sample of the facies based on these large sections, but internally in more detail with the microfacies, you can see clearly the accumulation of the forams. Also here in this last package, we can see occasionally crossbedding. This crossbedding has been interpreted as 2D dunes, but muddier compared to the previous one. In another subbasin, Calabasas, coeval deposit have been identified with thinner contourites or calcarenite beds, but with very similar characteristics, okay? Sometimes cross-lamination, cross-stratification, and again, in the calcarenites, in the fine sandier deposits, the accumulation of the forams. So, in summary, we have evidence of bottom current at different edges. The paleography of the paleo margin was an active margin, because we have the subduction south of Cyprus. But at that time, in the sandy contourite, we have many evidence of sedimentary, of extraction, sedimentary structure with lamination, irregular bedding, lenticular and wavy beds. This banding of bedding, very characteristic of these facies that we interpreted like ripples or small dunes. We have the concentration and or reworking of forams. In some beds, it's really grain-supported microfacies, so it's grain-supported texture because the accumulation of the forams. Perturbation in the contourites, in these sandy contourites, is through the deposits, but with some particular traces in some intervals. And in terms of porosity and permeability, in Petra 2, the porosity, primary porosity is up to 14%, with very good continuation of the beds, or these packages are very tabular. But in the most proximal section, the porosity is nearly zero because of the genetic processes. But the secondary porosity could be very high, could be up to 40%.
5 minutes, Javier.
Okay, thank you. So turbidites, they are, they have erosional base and also erosional or truncation top surface. They are muddier compared to the contourites in this example, in this case, and perturbation are from the top of the beds toward the base of the bed. Innofacies have been really key to understand the changes in the environment conditions, okay? Smaller grain size variation, small scale hiatus, evidence of condensation, emission surface, really identify higher frequency variation in these bigradational sequences in sedimentary processes, current velocity, and sedimentation rates. That really highlight that bottom currents at different scale are not permanent or semi-permanent processes. They are really intermittent processes. So what about the model analogs for Cyprus? So, well, bigradational sequences, as I said, they are very common on the reef. These ripples and small dunes are very common within Contourite channels. For example, this example from the Gulf of Cadiz, but we cannot see really any channelized bodies in Cyprus. But also, these ripple and dunes, small dunes, are very frequent on Contourite terraces, as Elda showed it to us during her talk. So perhaps this model is more similar to the deposit that we can see in Cyprus. And here you have another example of these Contourite terraces in sandy Contourites, in carbonate compositions with a small and bigger dunes. That could be an analog. Okay, can we see offshore similar deposits? And the answer is yes. In the Cyprus basin, we can see a sample of this plaster drift in edges equivalent to the deposit that we have seen and studied in some detail on land. And also locally in some of the subbasins offshore Cyprus, we can see Contourites. For example, this example from the West Eratosthenes subbasin. And here you can see Contourites also in the late Oligocene and early Miocene with these moats and adjacent Monte Drift. So we have, by this time, very active circulation, perhaps with weak or in general regionally weak currents. But why did change in the paleocurrent from the Eocene, Oligocene compared to the Miocene? So based on our paleo reconstruction, we understood that the shallowing of the Indian gateway generated an inversion in the current, especially in intermediate levels. So when the gateway was shallower than 400 meters, we started to have an intermediate current flowing from the Mediterranean into the Indian Ocean. So that was happening by that time, not before. Before in the Eocene, we have an outflow from the Indian Ocean into the Mediterranean. So that inversion in the paleocurrent could be associated to this shallowing in the seal related to the gateway. And finally, very briefly, associated to the 4 Deep Water Circulation Conference, we are offering a field trip in Cyprus, mainly to see these deposits. So the field trip will be for 4 days, from the 11th to the 15th of September. So it's organized by the Drifter Group for the conference. And the main objective is to visit all these localities, to see the Contourite deposits and the reworked turbidites, and to share with you all the information about the sedimentary aspects and also microfacies, ignophacies, and to discuss the ancient model with the modern day models. And this is the main aim. So this is the organizer of the field trip. Is Eiko Huneker, Rodriguez Tobar, Francis Rodriguez Tobar, Estefania Llave, Ancho Meno, Olmo, Mingue Salas, and myself. And the plan, briefly, Rachel, I am finishing only half a minute. For the first day, we will go to Petra 2 to visit the Petra 2 Romino section. In the second day, we are planning to go to the Agio Nicolaou section. In the third day, we will go to Calabasas. And finally, in the fourth day, we will visit other outcrop in Cyprus, more related to the Troodos massive ophiolites. And also, we have time to see the amber deposit on top of the oceanic crust. And also to visit some historical sites in Cyprus. Every evening during the field trip, we'll have a discussion section about that we have seen in the field and other conceptual aspects for Contourites and reworked turbidites. So this is the venue, it's the Hotel de Royal Apollonia. I hope you all join us on these amazing field trips. And that's it. Thank you for your attention. And thank you, Rachel, for your passion with me.
No, thank you, Javier. It's lovely to get a glimpse of the field trip, and you can absolutely count me in. It looks absolutely fantastic. Can't wait to see them. Any quick questions in the chat, then do let me know. So one thing, I don't know if we do know this, but do you have any idea of what sort of velocities we're looking at that have deposited these carbonate contourites?
The velocity, well, depending of what kind of deposit, because we have different deposits, so not all the biogradational sequence are the same, not all the contourite deposits are the same, but the velocity is not very high because mainly it's the reworking of the forams, and most of the time they are complete, they are not broken. Sometimes they are broken, but most of the calcareous deposits, the forams are not broken. And as you know, the hydrodynamic behavior of bioclast is different compared to siliciclastic particles. So I would say that weak currents could be enough to really remobilize the sediments. I'm talking about current that could be between perhaps 10 centimeters per second, maybe 15 centimeters per second, but not higher than that. Perhaps a little bit higher in this example where you can see the dunes, you know, but not as higher compared to the siliciclastic deposits, I would say.
No, excellent. So I see that there's some questions coming in, but I think we'll save those for the discussion.
Okay.
There is discussion on running 5 back-to-back trips so that we can get everybody that possibly want to go to Cyprus out there. I don't know if how that makes you feel, Javier. We will see. But
Okay.
thank you very much for a great talk.
Okay. Thank you, Rachel.
Excellent. So I will invite up our next speaker, is Mike Clare. So Mike, you can go ahead and share your screen. So Mike is based at the National Oceanography Centre down in Southampton, where he studies the impacts of seafloor currents on sediment transport and how it affects critical infrastructure and also pollutants, where the pollutants go in active deep sea systems around the world. So Elda alluded to the fact that we need lots more data from the oceanography point of view. And Mike's going to give us an overview of the advances in monitoring bottom currents.
Well, thanks very much. Do you hear me okay, Rachel?
Yeah, I can hear you. You're good to go.
Excellent. Very good. Okay, well, thanks for the invite to give this presentation. I promise no answers and hopefully lots of questions. And want to acknowledge the list of co-authors and collaborative or collaborations with different organizations from around the world. This really is a collaborative endeavor. And to share some thoughts and some data from direct measurements of bottom currents. And that's really kind of looking down at the seafloor. So we've had some discussion on why we care about bottom currents in a general sense. Why we care about making direct measurements. I think Elda really started to get to the core of this question. We typically use either morphology of the seafloor, so bed forms and other features that have been sculpted on the seafloor to reconstruct past bottom currents, particularly their locations and their velocities. Very widespread is the use of sortable silt as a proxy for paleo reconstructions of past near-bed current intensity. But McCabe et al. In 2017 and others since have demonstrated quite clearly that there's a need for site-specific calibration of this proxy, and no universal law yet exists and may never be possible. So there is a need to calibrate these measurements. And indeed, we try and reconstruct the orientation and the nature of bottom currents from other aspects, such as the architecture of offset submarine channel deposits. But several studies, such as this by Pamela Sampson offshore East Africa a few years ago, demonstrated that very similar architectures may result perhaps from completely competing directions of currents. And so if we want to start to use the models like Elda and Henriette have been presenting these fabulous 2 and 3D numerical models, then we have a need to both test and calibrate those models. And then we care more broadly because bottom currents are now accepted as being important for transporting nutrients and carbon and pollutants. And that has implications for biology and understanding the fate of the materials and waste that we produce. But also because those models are also used for designing resilient infrastructure. such as pipelines and cables across the seafloor. Indeed, here's the global network of more than 1.8 million kilometers of fiber optic cables that span the ocean, and abrasion and chafe relating to bottom currents can damage those cables. So it's important to be able to design cables to withstand those sorts of impacts. So in this presentation, I'm going to take you through a few sites. I'm going to cheat a little bit because some of these are really related to Contourite systems, such as off East Africa. In other cases, these are areas where topography has steered bottom currents. So perhaps we have internal tides within submarine canyons. But I want to share some observations, some challenges that have been identified by previous studies, and try and talk about where I think future efforts should be focused. So Henriette showed these fabulous data from offshore South America. And so these are measurements made with acoustic Doppler current profilers, in this case deployed from a vessel, a much larger seagoing vessel than this little one, but a similar concept as is used in rivers. And ADCPs shine usually 4, some cases 5 beams down towards the seafloor, or if they're on a platform on the seafloor, they look upwards. And based on changes in the Doppler shift, we can reconstruct the 3D velocity structure of currents. So we can get a vertical profile through the water column. We can see how fast currents are moving and in what direction. We can also take information such as the backscattered energy that's returned at different elevations within the water column. And that acts as a proxy for helping us understand what suspended sediment concentrations exist. It's not that straightforward, but it's pretty much that's how it works. So these observations, based on ADCP measurements made from a vessel, provide us with these really useful spatial footprints of how diverse the directions and intensities of bottom currents can be, and how they vary in response to local topography and other oceanographic controls. There are a couple of limitations with this. So these are super valuable measurements, as Elda has emphasized, but the frequencies that you need to get all the way down to the seafloor are quite low. And so these give us, 1, quite coarse vertical bin sizes, and 2, they limit imaging within about 150 meters of the seafloor. So when we say near bed, we're getting closer to the bed than other measurements have allowed us to do, but we're still not right at that benthic boundary layer. And the other shortcoming of these measurements is, whilst they cover a very big spatial area, the measurements are opportunistic. So they're taken over very short time periods. So if we're starting to want to calibrate models or longer term depositional reconstructions like Javier is talking about, we need longer duration measurements, and we want to get really close to the seafloor. So I think to complement these measurements rather than competing with them, we also need detailed time and depth resolve measurements of bottom currents right as close to seafloor as we can, as well as measurements that capture the water column and the physical oceanography. And we want to then link them to suspended sediment concentrations, to the deposits that they leave behind, to the morphology that they sculpt, and then in turn to help us understand how the stratigraphic architecture resulted. And on top of this, we also want to understand how biology responds to it, both in terms of understanding what role biology plays in shaping and reworking deposits, as well as what the implications of these currents and the material they transfer has for biology. So in the past few years, a number of studies have demonstrated that this is entirely doable for turbidity currents. It's possible to measure turbidity currents that move at several meters per second and use high-frequency ADCPs, either suspended on moorings above submarine canyons or founded on cabled observatories on the seafloor, and to get very, very resolute temporally. In some cases here, a flow measured in the Congo Canyon that's up to 80 meters high, measured at a resolution of about 1 meter vertically, and with measurements made every 5 seconds. So we can get some really detailed insights into sediment transport and the interaction of these currents with the seafloor. So we use instruments like this little yellow guy here with a black helmet on. This is an acoustic Doppler current profiler that's pointed down towards the seafloor and then housed within one of these positively buoyant syntactic buoys that keeps this ADCP nice and straight, looking downwards, and a couple of train wheels down on the seafloor for the anchoring. And so here, through time on the x-axis in seconds, and then in depth on the y-axis, we can record the velocity through time, or in this case, the echo intensity, that tells us something about the suspended sediment concentration that these flows move. And so this sort of approach has been demonstrated successfully for bottom currents, and it's no surprise because they're generally lower velocity than turbidity currents and carry less sediment, so easier to measure. This great work in the South China Sea by Zhang et al., and then more recently by Zhao et al., looking at the same mooring, looked at a 75 kilohertz ADCP, suspended a few hundred meters above the seafloor, a sediment trap that caught the material in a funnel that was being carried by flows near the seafloor, and made these excellent long-term measurements. So here we're looking at several years worth of measurements of bottom current velocity that's vertically resolved. We can look at temporal fluctuations in suspended sediment concentration, and look also at temporal fluxes and switches in the orientation of these currents. And so this one mooring on its own was used to suggest that there are very seasonally variable mesoscale eddies in the South China Sea. But again, there are some issues with this. This is fabulous data that gives us very new insights. But the instrument that's used is quite a coarse resolution oceanographic instrument. So the bin heights are broadly 16 meters. We don't get much closer than about 30 to 40 meters towards the sea floor because of this side lobe interference zone. So we still have a need to get closer towards the sea floor. And that one mooring on its own also doesn't allow us to understand the broader, bigger spatial variability of currents. So whilst it might be easy to measure bottom currents, it's difficult to characterize them over long time periods, big spatial areas, do the water column, and get close to the sea floor. A study published last year by Arne Fuhrman in East Africa, looking at northern Mozambique, looked at a mixed system where turbidity currents have previously shaped submarine canyons, and showed using high frequency ADCPs, so 1200 kilohertz ADCPs, that we could measure bottom currents and measure very close to the bed within a couple of meters of the sea floor over a period of more than 12 months and with a vertical resolution of about 25 centimeters. And so here Arne demonstrated that these currents are dominantly moving towards the north, here as shown by these blue arrows, although there's quite some variability. And this is just information from the bottom bin close to sea floor. Currents are highest in the shallower water. So here, just down dip of the shelf break, currents locally reach or exceed 1.2 meters per second, about 5 meters above the bed. So very capable of resuspending and eroding sediment here, and are topographically steered by the very steep shelf break. So Arne also showed that these bottom currents, whilst they are generally moving towards the north-northwest, north-northeast, that temporally they're very, very variable. And I guess this will lead into Dorrik's talk after this one, is over this long time period, we get this overall sense that this is the prevailing direction of the current. But were we only to have made measurements over, let's say, a week or two, we would only have to be in one small time window here, for example, where we get a completely contrasting direction, and we'd interpret these currents perhaps in a slightly different way. But these long duration measurements that were made close to bed matched very closely also with detailed observations of the morphology of the sea floor. So here we have a 60 centimeter bin size bathymetric surface, and this was acquired using a remotely operated vehicle, and showed these obstacle and comet scour structures as well as these linear furrows. And the measurements that were made of the bottom currents actually match very well with Stow et al.'s bedform velocity matrix, which is reassuring. So those sorts of proxies seem to stand up quite well, at least based on this observation and others in a few other sites that I've seen. But these bedforms are only imaged with this high resolution bathymetry acquired either from an ROV or an AUV, and the hull mounted bathymetry in this sort of water depth in about 1500 meters water simply aren't visible and don't show. So I guess the point I want to leave you with here is that these currents can be quite temporally variable. I think we knew this anyway, but this is kind of demonstrating this with direct monitoring data. And so not just the spatial footprint of your measurements matter, but also the time window over which you measure is very important as well. But these measurements have been very useful, and we've started then to link this to the deposits in the stratigraphic architecture. And Anna nicely showed in this study that the contourite drifts are basically stepping upstream, creating these laterally offset stacked channels, which are making their way back up into the direction of the oncoming bottom currents. And interestingly, we published this study, and I think it came out in the same issue of Geology as Elda's study, working in the Eurotank with Joris Eckenhuis and others, that showed a very, very similar conclusion. So reassuring that bottom currents and also physical modeling can be used to come to independently to very similar conclusions. For the same study, we also found, this is the shallow water near the shelf, and then down here in almost 2,700 meters water depth, these measurements of bottom currents don't always show obvious synchronicity. Where we see these peaks in velocity, we don't see them necessarily at the same time at different moorings. And so we attribute this to spatial variability of eddies and other variations, spatial variations in the current intensity. And so clearly 3 moorings is not going to be enough for us to understand the detailed spatial footprint of the bottom currents, which can locally be very, very strongly steered by the topography, which can be quite severe in that particular area. So now I'll lead on to some of the implications of and emphasize really why we need more direct measurements of bottom currents. It's now well established that pollutants, particularly plastic, is transported across the ocean surface by surface currents driven by Stokes drift and waves and other controls. So this work by Erik van Sibeli et al. Is a Lagrangian particle tracking model which shows red plastic released from terrestrial sources and then run over several decades, and showing it becomes concentrated within these subtropical and other gyres. But surface plastic is only accounts, or it's estimated to only account for less than 1% of all the plastic that's ever entered the ocean. So more than 99% goes unaccounted for. And it's now increasingly recognized that currents within the water column are responsible for advecting plastics as well as other pollutants across the global ocean, and that currents near the seafloor play an important role in dictating where they ultimately end up, so what their fate is, where they will concentrate and accumulate in the seafloor. So here's a study with Ian Kane and others that we published last year in the northern Tyrrhenian Sea and the western Mediterranean, that showed how seafloor gyres are very capable of sorting microplastics, so that the size fraction that's less than about 1 millimeter in size, and preferentially accumulating those plastics in the areas where sediment is preferentially accumulated. So inhibited accumulation within moats and preferential deposition within areas of mounded contourite drift. And so one of the conclusions of this study was that, at least based on one study, and so more is needed to be done, is that contourite depositional systems might be preferential areas for the sequestration of microplastics, certainly compared to other depositional systems in the marine realm. So far, this seems to be the case, particularly microfibers, so these tiny fibers that can come off clothing and from other purposes, were being sequestered within contourite mounds. We found no relationship between distance from coastline and the amount of fibers or fragments. In fact, we found that they were generally focused within the depth range, the water depth range, where bottom currents are focused. And so we linked this to numerical modeling work by Elda to conclude that it's bottom currents that play a significant, that have a significant control on where these microplastics end up, finding that they are inhibited in terms of their accumulation within moats where shear stresses are very high. But adjacent to that, where we see expanded stratigraphic sequences, we also found the highest concentrations of microfibers. In fact, the highest anybody's found on the seafloor to date. And so this intuitively matches with what we'd expect, but was the first study to show it. And so I think further studies that aim to make these links will be useful, not only to understand where pollutants end up, but also to investigate the potential for things like microplastics as a proxy to reconstruct bottom currents in the same way as oil slicks, for example, have been used to reconstruct surface loop currents in the Gulf of Mexico and other places. So direct measurements were used, although fairly limited direct measurements, to calibrate the numerical modeling, but there's clearly more work needed to be done to help us understand where maybe other pollution hotspots are. But microplastics has the potential to be a possible tracer. We just need to understand more about its behavior. We found that there's a threshold shear stress above which microplastics don't accumulate. So in the moat, they can be flushed along slope, or at least lofted and pushed towards the moats. But it's very important to understand how intense bottom currents might get in the future on a seasonal basis, decadal, and maybe over longer time scales, because the microplastics that have accumulated at the seafloor, we found that they're very close to the initiation of motion, at least taking a Shields type approach. And so this means that maybe they're not sequestered for a very long period of time. Maybe they will be flushed and moved to somewhere else. So for fragments, we found that there was quite a clear threshold of bed shear stress below which they accumulate and above which they are flushed or at least not allowed to accumulate. So getting more direct measurements to better understand bottom currents, their distribution and intensity near bed is particularly important for this purpose. But also because they carry organic carbon and nutrients. And so often areas that experience elevated bottom currents, particularly trapped within submarine canyons, such as Monterey Canyon here, where internal tides pump up and down the canyon on a tidal frequency, or around seamounts, are also areas of high biodiversity. And that's because they're bringing in these food stocks of carbon and nutrients. So this work by Katie Meyer didn't look at contour currents, but it looked at internal tides within the Monterey Canyon and demonstrated using very high frequency instruments, again, 300 kilohertz ADCPs, about 60 meters above the seafloor looking down. And so Katie here shows measurements made 10 and 65 meters above the seafloor and demonstrates how quite often internal tides can reach velocities exceeding several tens of centimeters per second, and in some cases exceeding a meter per second. So certainly capable not just of transporting nutrients and carbon, but also exhuming material that was previously buried in the sea floor.
5 minutes, Mike.
Thanks very much. We can start then to link this to the sediment that they carry. So these are sediment traps that were sited, in this case, 35 meters above the seafloor at 200 meters water depth. And so here the whites are high density, this is sand, and the grays are mud. And what we found from this CT scan, just to zoom into this section here, is that none of these deposits represent turbidites. These all represent suspension or resuspension events, the whites, in relation to tidal frequency internal currents or waves within the canyon. And previously, I think I would have interpreted this as something like a fine-grained leve type turbidite accumulation. And instead, these solely relate to the internal tides within the canyons. And Monterey Canyon's far from the only canyon that has this sort of behavior. This is a mooring at 1,500 meters water depth in the Whittard Canyon. And so here in red, we can see near bed currents that are racing up the canyon up to about a meter per second, like a bore, then the velocity dying off, and then the current returning down the canyon and then racing back up the canyon again. So clearly more than a meter per second at times, capable of not just transporting carbon, but also eroding seafloor sediments. So these bottom currents are important, as I said, for transporting all sorts of particulate material and sustaining benthic communities. And that mooring in the Whittard Canyon is located just adjacent to this vertical wall, which has a whole host of Lophelia cold water corals. So there's an intimate linking between biology and this deep water sedimentology. So hopefully I've at least set out a case for why we need more measurements really near the seafloor for bottom currents. There are other opportunities as well as using ADCPs and using other instruments such as current profilers. And so some exciting work actually using cables themselves to make distributed acoustic sensing measurements, which is possible over distances from shore of about 100 to 200 kilometers based on existing technology. And so this work offshore California by Nate Lindsay, published in Science a couple of years ago, demonstrated how ocean processes can actually be heard and recorded by fiber optic cables. So maybe we could do more with the existing network of cables to listen for sediment transport events, tidal bores. Maybe we can hear internal tides within canyons. But all this work needs fingerprinting. So to finish up, it's definitely possible to monitor bottom currents. It's relatively easy to do it at an individual location, but long duration and big spatial footprints are the challenges. So there's a need to integrate all the different observations and measurement technologies that we can. We can use gliders to get relatively short time period, but very detailed, very, very spatially comprehensive measurements, as well as moorings or seafloor based measurements. I think we need to think about now characterizing different contourite subdomains in mounds and moats and sheeted drifts, for example, really testing what's the influence of local topography and what are we missing from existing models that don't capture that fine scale bathymetry. Vertical resolution is really important. And so I think we need to both capture full water columns, so quite low frequency measurements, with very high frequency near bed measurements. And then think about what we miss when we're making vessel-based measurements for a few hours or days, when we're making measurements with moorings over months or years potentially. And then how do we link that to the depositional record? Clearly, there are going to be events that are not going to be caught by the monitoring event that we're looking at. And then finally, thinking about biology. So here we have a time-lapse video taken every hour for 47 days in an area that's affected by tidal currents west of Shetland, so northwest, offshore northwest Scotland. And here we can see a whole variety of different depositional events. And we can see it's not just the bottom currents, which are switching in two directions in response to tidal controls, but the biology itself actually serves to clean up much of the seafloor, to rework material into different parts of the seafloor. And also understanding what role bottom currents have on important ecosystems, such as this sponge here, for example, is going to be important, as bottom currents may change in response to ongoing and future climate change. So I think more of these observational data sets are needed, and I think they're starting to come online, and then we can hopefully do something useful with explaining how bottom currents work really close to the seafloor, as well as in the water column itself. Thank you.
Super, thanks, Mike. That was a great video at the end there as well. Fascinatingly busy down there. We've already had quite a few questions come in, so I'm going to go straight to the questions. So Dorrik asks, is going back to the plastics, microplastics. How do plastic fibers and fragments get into the deep sea, and how quickly do they fall? Do they flop like other parts?
It's a really good question, and the answers are unclear. So a lot of the studies, that particularly the ones focused on looking at surface plastics, have made a lot of gross assumptions about the settling velocity of microplastics. So more than 50% of plastics actually are produced with a density that's higher than that of seawater. So they naturally sink, or at least they're not positively buoyant. But increasingly, it's recognized that biofouling plays a very important role. And so that can increase the density or the weight of the plastic, and so it will start to drop out. The microfibers one is a real kind of question, because it's not just in the deep sea we're seeing abundances of microplastics. In many rivers, they're seeing them preferentially sequestered as well. And seemingly, you should just be able to transport these easily and they wouldn't end up in bedload. Florian Pohl had a paper a couple of years ago that suggested that these microfibers actually get trapped between grains. They can get stuck to kind of clay agglomerations. They can become ingested by fish and other organisms and then be expelled as fecal pellets, which have a higher settling velocity than the original microfiber. So we don't really know. And there's a lot of work being done on the chemical and physical behavior of microfibers, microfragments. I think there's some novel work that's being done by people like Roy Wargelius at Manchester and others in actually looking at the aging of plastics. So whether you can actually look at the degradation of the different polymer types and then link that to the age. But that's also dependent on the environment, the temperature, the oxidation conditions. So it's complicated is the easy answer to the question.
You may have answered the next question in there as well. So is there a way to age date these microplastics so we can understand how long they've been within these systems, currents and sediments?
People are looking at it. So there's work that's done from a kind of a polymer degradation side of things. There are other people doing physical experiments where you age plastics in different settings. And Stefan Kraus and others have been doing some really novel work with annular flumes in rivers where they set up long transport experiments in an annular flume to see what happens in terms of the abrasion and the breakdown of these microplastics and what they look like after you've transported them for several kilometers. But I've not seen any of that work done for, contour currents, for example. So if someone's got a flume tank that they want to fill with loads of microplastics, then there's lots of exciting questions to be answered there, because those sorts of things then inhibit our ability to use them as a tracer. So we're definitely not there yet.
Yes, it definitely, all the things you talked about, very reliant on lots of funding. And this leads me nicely to Michele's comment. There's we're lacking many studies with multiple moorings on a single contourite system. It's probably due to cost. So yeah, definitely scope and possibility to join forces in the future. So it's a really exciting area of research, I must say, Mike.
Yeah, I think that's key. I think force multiplier is absolutely right. So if someone's got some ship time, so we're from the National Oceanography Centre, we have ship time, but we have like one mooring in the Wittard Canyon, we have one mooring in the Porcupine Abyssal Plain, and we have one mooring in the Darwin Mounds where we capture internal tides and bottom currents. And we can keep that going for 5 years or so. That's fine. But we worked with Furuminis at NEOS, and she had 2 separate moorings in the Wittard Canyon. Suddenly you have, 3 moorings. And so I think those collaborative opportunities are there. The other thing I would stress is the sorts of data that we get at the National Oceanography Centre is to acquire data to allow other people to answer research questions as well. So those data are being gathered. So if people do have questions that they want to answer or they want opportunities to go offshore for research, then do reach out, because spinning up collaborations is part of what this is supposed to do.
Yeah, super. Thank you so much, Mike. Really great talk. Very interesting stuff. And I'm sure it will be a topic of conversation in the discussion section. So thanks, Mike. We're now going to move on to our final speaker of the evening. So I would like to welcome Dorrik to share his screen. So Dorrik is an emeritus professor at Hernández-Molina University and also a distinguished professor at the China University of Geoscience in Wuhan. And he will be chairing this meeting in September once we get to Edinburgh. Now, Dorrik's been working in Contourites for over 4 decades, so hopefully he knows what he's talking about today when he talks to us about Contourite cyclicity and processes. Take it away, Dorrik. So I'm not hearing your voice yet. Are you muted? Am I able to unmute you?
Is that better?
Yeah, I can hear you loud.
Good. Thank you very much, Rachel, and thank you to all the participants for hanging in with us. I must say the talk's been absolutely fascinating so far. I'm very, very surprised that they've all kept to time, so I'll try my best as well to share just some recent work with you, both mainly based at the marine level, some informed by work on land as well. And I must acknowledge first and foremost, much of the work is carried out by the team here of research students and associates and colleagues at Heriot-Watt University, but also in collaboration with places elsewhere. I'm going to focus right in on the sediment scale of things. I can advance the slide. Yeah. And give you just that snapshot of current research, looking firstly, as I say in the title, at Contourite sequences and the possible cyclicity of those sequences. And then in a little bit more detail about what we can infer from trying to correlate sequences between sites by looking at really detailed characteristics of those Contourite sequences, grain size, fabric, and other facies. I may touch on hybrid facies, but probably leave that for discussion. Those of you who have listened to SED's online talks before may have heard me talk about some of these things in the March talk in 2021. That's still available. Some of this material is published in Stow and Smiley, but then 2 papers will come out, we hope, in the Marine Geology special issue, virtual special issue that we're currently publishing. One first authored by Pan et al., one of my students, and one by myself, and some in some of the other papers. But without further ado, let me move on. I'm going to focus a fair bit of what we've done back on the Gulf of Cadiz and what I call the Contourite Laboratory, and what Javier and I and several other people went to investigate in quite some detail with IODP Expedition 339 nearly 10 years ago now. But still there is a huge amount of data coming out of this work and a huge amount still being worked on. The map in the top left shows you the different sites that we drilled under the influence, more or less all under the influence of that Mediterranean outflow water. And I'll focus in particular on a few of those sites. The more distal sites, 1386 and 87, a sort of medial site, 1389, and allude to some of those proximal sites, proximal areas, 1388. The 2 seismic profiles there, the top one shows you the mounded drift and the associated moat associated with sites 1386 and 1387 at the distal end, a big, mainly muddy, silty drift. And the lower seismic profile shows you one of these abraded surfaces in the more proximal area. Throughout the region, and particularly in the more medial and distal sites, we repeatedly came across these bigradational sequences of contourites shown in a core on the right-hand side there, and you see the 10 centimeter scale for showing you the length of the section that we're dealing with. And I've highlighted the C1, C2, C3, C4, C5 contourite divisions of that typical bigradational sequence. Some people question, and it's right to question, whether we're really dealing with contourites. And I think we have to all stand back in whatever work we're doing and saying, are these really mainly driven by bottom currents? Or, as we've seen in some of these earlier talks, are they in fact hybrid processes that are operating and hybrid deposits? And I think you have to approach that question and that questioning at the 3 scales that I've shown you there. We believe in the Gulf of Cadiz that they are contourites because at the very large scale, we've got that oceanographic system where we can measure the currents, we can detail the direction, the speed, the location, the characteristics even of those bottom currents. And they're in a tectonic setting close to that Gibraltar gateway and hugging the continental margin that allows us to be fairly confident of what we're dealing with. The second and the sort of medium scale of of identification is to look at the seismic processes. Do we have those big mounded drifts? Do we have the abraded platforms, the sheeted drifts? Do we have large scale, extensive hiatuses through the record and so on? And yes, we do in this particular case. And then we can look at those sediment characteristics. Do we have the bigradational sequences? Do we have all the other sorts of features that I'm going to talk about shortly? So I hope I've convinced you that we are dealing in the most part with contourites here. I'm going to talk about the sequences now briefly, and to see if we have any cyclic repetition, systematic cyclic repetition of those sequences, what we call cyclicity. And Javier Pan has been working on this in particular for his PhD thesis. And so much of this data comes from his work, part of which is published or was pre-published in the BSRG meeting and is in review for the current situation. The top left diagram there shows you a series of these contourite sequences through the top few hundred meters of one of the sites, site 1389, in fact, a medial site. And you can see what we mean by these bigradational sequences, or indeed other sequences. The two highlighted in red are the ones that we have most data from, and those are classic bigradational sequences from mud to silt to sand, back to mud, back to silt, and back to mud. But many of the other ones you will see are either smaller, are partial sequences, are bottom only, are top only sequences, or are more complex. Note the scale there of 10 meters. So the sequences we're looking at are a few meters in order, and some of them, of course, much smaller, some of the complex ones much more. We've looked at or counted, I say 800 sequences. It's actually well more than 800 sequences now at those three sites in the top 1.5 million years of section. And those top 1.5 million years we take because we are very confident that bottom currents were dominant, absolutely dominant at that time. Where you get back a little bit older than that, and certainly pre 2.5 or 3 million years, then we're rather mixed with other processes as well. The average thickness of those sequences, 2.5 to 3.5 meters, and we can calculate based on average sedimentation rates that the mean duration is 8 to 12,000 years. But you see on that frequency sequence duration histogram on the right-hand side that there is a big range of sequence duration from 2 to over 20 million years, 1,000 years of duration. A sort of average mean duration of that whole thing between about 8 and 12,000 years, but a mode you can see maybe 4 or 6,000 years. We'll come to why that might be in a moment. Now, one of the things to try and assess is whether we really do have that sequence C1, C2, C3, C4, C5 as a typical and a repeated sequence style. And in fact, by doing transition probability matrices for this site and for 1386, 1388, for many, many hundreds of meters of section and many hundreds of sequences, certainly the C1, C2, C4, C5 sequence is the most common. In other words, mud to silty mud and back to mud again. In some cases, we have C3, the sandy division within there. But it's not absolutely dominant. It's the most common, but there are other sequences that are there as well. Now, in terms of correlation, I was expecting that we would have exactly the same sort of sequences at every site we drilled, certainly within close proximity to each other. But that turned out to be not quite the case. And these diagrams here show what I'm talking about. On the left-hand side, to start with, we have holes 1386A and B down through about 100 meters from top left to bottom right there. And the sequences shown schematically for you. Now, those major sequences do correlate between the A and B holes, which are about 40 meters only apart on the sea floor. But many of the minor sequences don't appear to correlate very well. So there's a fairly good correlation of many of the sequences, but not perfect. The same applies to the right-hand diagram there, 1387, A and B, again about 40 meters apart, and perhaps moderately good correlation of some of the sequences, but certainly not of all of them. And then if you try to correlate between 1386 site on the left and 1387 site on the right, the correlation is fair, but goes down in quality. And I base those comments on a statistical assessment of the correlation between those two different sites. And I think the lack of perfect correlation certainly informs us about, if you like, something else that's happening there. Local bottom current variability, eddies, vortices, topography, that is not giving a uniform spread of sequences across the whole. What I should have said at the beginning is actually I'm going to throw more questions out than I'm going to give answers here. And whereas sequences, and these bigradational sequences may be a defining feature of Contourites, and I hasten to say in many, many different drifts around the world, not only in the Gulf of Cadiz. But why are the sequences so irregular in nature and cyclicity? Yes, we do have some different scales of broad cyclicity that's evident from our statistical analysis at about 400,000 years, 100,000 years, and even more significantly at about 20,000 year cyclicity, linked clearly to orbital climate change. But the mean sequence duration is none of those. It's 8 to 12 kilometers. The mode is 4 to 6. So maybe we're missing something. Controls on the sequence formation, certainly climate controls, and we do recognize particularly that 20,000 year cycle. Current speed variations linked to climate, sediment supply somewhat independently, but is there something else we're missing? And I leave that question open. Now, we plunge down in much more detail on the sequence anatomy of this standard bigradational facies model that's shown in detail there for you in the middle, the C1 to C5 divisions, the big variations that we have on that with top only, bottom only, mid only, and mid missing divisions. But throughout the Gulf of Cadiz area, and in many other cases, we have the typical other diagnostic features of Contourites, the generally uniform, monotonous, if you like, color, composition, texture, general absence or rarity of primary sedimentary structures, abundant bioturbation, and these different bigradational sequences. It's a mixed bioclastic to originous composition that's typical, in some cases slightly more bioclastic, in other cases much more siliciclastic. But we have done many, many detailed measurements, and I'm only going to highlight a few for you in the short time I've got. And this is particularly on the grain size characterization through those, through one of the two sequences that I was telling you about. And this is sequence 25X from core 25X, about 5 meters thick. We have the C1 to C5 divisions shown in red on the left of those grain size heat maps, which is a way of illustrating very graphically the change of grain size through these sequences. And you can see essentially the redder colors and the orange colors show a higher percentage of that particular grain size, and the grain size scale is shown along the bottom in a logarithmic scale in micrometers. And you can see very clearly there the increase and the decrease through each of those sequences. through that one sequence, both using bulk grain size distribution, and then if you dissolve out the carbonate and have the carbonate-free grain size distribution. On the right hand, in the little blue diagrams, you see smooth frequency curves of grain size distributions. And you can see, for example, at the top and the bottom of each of those sequences, a much broader spread, poorer sorted, muddier sediments, and then becoming better sorted, narrower, sandy, silty fraction in the middle of those fractions. The slide on the right, just mentioning that very briefly, has broken down the grain size into different fractions. The clay, very fine silt, medium and coarse silt along the top, and the sand sizes along the bottom. And the blue and the red give you a bulk and a carbonate-free measurement. And all I want to say there are two things. One is you see very clearly that bigradational sequence. And then secondly, you can see a very clear grain size oscillation at a smaller scale. And you can see that particularly, for example, at the medium sand, fine sand sizes, where you have in the bulk fragment, in the red curves there. And that grain size oscillation of about 30 to 70 centimeters per second. Sorry, centimeters thickness. We'll come back to what that means. Now, another thing that we've observed very clearly, and we've worked on a little bit and trying to understand, are the breaks in the sediment record that we call emission surfaces. And their emission of sedimentation, lack of sedimentation, or erosion, small-scale erosion of sedimentation that occur during a particular sequence being deposited. And this was first shown very graphically by Rachel et al. In the 2018 paper with the CT scan shown in the left there, an associated core photo, where you have very fine grained muds in green going into silty yellowish colors and red sands. And then a fairly abrupt break, an abrupt boundary, that emission surface, before we get back into the silts and the muds. Now, we looked for these very carefully in the two sequences from 1389, and I show you just the sequence in 25X. And I show you the grain size plot, their mean grain size through that sequence over 5 meters or so, from 220 to 225 meters below the sediment surface. And you can see, as we've shown in the dashed lines there, clear sudden breaks in grain size rather than a sort of smooth continuum. And we interpret those as these emission surfaces. And then if we try and expand that record, as I've done on the right there, and join those lines up with a smoother curve, now one may argue whether we should or should not do that, but join that up with a smoother curve, then the amount of time and material that's missing have been highlighted in those pale orangey yellow bands. And in fact, if you expand those emission surfaces, the hiatuses that are equivalent to about a third of the section. So instead of the section being, or that bigradational sequence being about 5 meters in thickness, it actually should have been 7.5 meters in thickness, and some of it has not been deposited or it's been eroded in those emission surfaces. So I think that's quite a significant observation to make, and significant in terms of trying to interpret what our currents are doing in terms of depositing the sediment. Okay, Rachel. So we've got much more data on grain size through individual sequences and composition and other features. But what causes those emission surfaces? Do they represent significant hiatuses with non-deposition or erosion? How long are they? Are we right in saying that they represent about 30%, a third of the section? And then what causes that grain size oscillation? And I told you I would ask you more questions and give you answers. So I would just tackle, I think, one in my remaining 5 minutes, one of the topics that I had. And this is using the grain size as a proxy for bottom current speed. Now, the diagram on the left there from Rachel's 2018 paper, modified by you, the diagrams from Rachel, but we have much more data that we've added to that in the paper by you in 2020. But what it shows us is on a plot of sorting, standard deviation against mean grain size, a very clear and systematic trend, however many samples we've got on this, that you can see there, that I call this depositional trend for Contourites. And it stretches, well, this sort of trend and this sort of characteristic was used first of all by Nick McCabe and others from 1995 and his more recent paper in 2017 to describe the sortable silt proxy as a proxy for current speed. And he uses the mean of the 10 to 63 micron carbonate-free fraction. Well established, well used by many people. But we don't see why we should not use the whole of that depositional trend between about 15 and 150 microns as a proxy for current speed. And so we've developed a new sortable silt and sand proxy that uses that full range. First put forward at the BSRG meeting 2019, and now in press again in the virtual special issue. And if we do this, let me just say very briefly, using that modified equation, current speed U is 1.25 times the mean of the SSS, the sortable silt and sand, minus 30 centimeters per second. Similar to, but different from the McCabe sortable silt model, we get what we think is a fairly realistic pattern of current speeds, flow speeds, through those two sequences, 11H and 25X. As you can see in the middle diagrams there, from very low speeds, less than about 10 centimeters per second for the muddy fraction, and then up to between 20 to 35 centimeters per second for the sandy fraction. I will not take you through the microfabric due to lack of time, but we can come back to that in discussion. I just wanted to leave you with the fact that we have referred to, and several other speakers have referred to, the fact that the deep water system is awash with different processes, the downslope processes of different types, the along slope processes, including the bottom currents that we're talking about, the pelagic and hemipelagic vertical processes. All these processes are operating and may operate together or interbedded or interacted, so that they overlap or interact with each other. And we must expect that facies continuum, process continuum, and hybrid facies to result. And certainly in the case of the Gulf of Cadiz, we are beginning to see that process interaction in operation as well, particularly at the fine-grained end, where we're interacting hemipelagic with bottom current or contourite processes. But again, more of that in discussion if we have time. And I would just point to the discussion session to some of the things that I've raised in this talk, that others have raised in the talks before me, and that are some of the key challenges that remain for us to discuss and to think about in contourite research going forwards between now and the conference next year, and indeed over the next 10 years. We'll come back to this list, I hope, during the discussion session. But let me leave you there, and Rachel, over to you. Any questions?
Oh, super. Thanks very much, Dorrik. We do have a question already in the chat for you from Jasper. So do you think that these astronomical signals, the cycles, could be better preserved in contourites or in turbidite sequences in general?
Right, interesting question. I think on the whole, well, I'm going to say in contourites, first of all, and then let me explain why. I think probably because contourites are a more continuous, although I've said there are hiatuses and emission surfaces, they're a more continuous sedimentary record. And then therefore they're going to show us a more continuous variation of climate-induced bottom current velocity changes and so on. Now, interestingly, having said that, I certainly have seen various work, and I've done various work myself, where turbidite variation seems also to follow orbital cyclicity in some cases. And I think that's particularly the case of fairly frequent turbidites and fairly fine-grained turbidites that are packaged together. But in answer to your question, I think the contourites gives a better and more refined signal.
Yeah. So another question, any idea about the drivers for the high frequency cyclicity?
Yeah, very good, very difficult question. And, you know, we have been thinking and searching for that. That a simple thing would be to say, we've got two prominent controls, dominant controls on those cycles, those sequences. And one is bottom current velocity speed change, and the other is sediment supply change. And the bottom current speed changes could be controlled largely by orbital parameters, say at the 20,000 year precessional cycles. But the sediment supply may be influenced by different processes at a different time scale. And it's the interaction of those two controls that gives us this fairly varied sequence duration and fairly irregular cyclicity, if you like. However, I would like to think we might find some other process. I call it ocean basin oscillation or something like that, that is something completely different that we've not yet thought of.
Yeah, I think this will be a really interesting topic of discussion in the forum. Welcome anybody's input on this as well. It would be really interesting. I think I will close the technical program there in the interest of time. So thank you very much to all the speakers. It was fantastic talks all around, really interesting to see some great data from around the world and looking at contourites at all scales really today. It's been very good. I'm now going to pass over to Øystein Nicholson at Hernández-Molina University, who's going to give us an update on the special issue that we put adverts out last year, and it is nearing completion. So Øystein, can I hand over to you, please?
Sure, just let me share my screen. Let me know when you can see this.
Yeah, you're good to go.
Good to go, okay. Yeah, so thanks, Rachel. And yeah, this is a good opportunity really just to give you an update, or the community an update on the state of this special issue, this virtual special issue that is in the process of being published, and I'll explain that in a moment. But the title of the special issue is Bottom Currents and Contourites, Process, Products, and Impacts. And you can see the editors and the editor-in-chief listed here. So this comes from kind of a long sequence of special issues on contourites extending right back to the early 90s, a series of sedimentary geology special issues edited by Dorrik and Faugeret, if I'm pronouncing that correctly, and then a number of others in the early 2000s, particular emphasis on this on the Contourites, special issue in development of sedimentology. And then 2016, I'm probably missing one or two here, but these are the ones I find while we're preparing this. The Contourite logbook in 2016 is the last marine geology, which was really a real broad scale look at Contourites, bottom currents, and their deposition products. And then we have a 2019 special issue specifically on carbonates. And there have been a number of others, special sections of individual journals. So here we are in 2021. It's been 5 years since publication of this Contourite logbook, and actually 6 or 7 years since most of the papers were really published originally. So we thought it was time to collate another special issue. And the key themes that we were looking for the special issue are listed here. So those extend from, if I just put my interruptions on, these extend from looking at and improving our understanding of processes in the deep sea associated with bottom currents, and how these relate to specific bed forms or seabed morphology. Active monitoring, or at least in situ measurements of oceanographic processes of currents, and how again these link to sediment dispersal in the deep ocean. Hybrid systems, modeling, again numerical modeling of process and product, geohazards associated with bottom currents and Contourites in particular, and also ocean gateways and their controls, so longer term controls on ocean circulation. As recorded in Contourites. So this is where this is at the moment. This was first advertised at the end of 2019. We had 53 abstracts submitted, 45 abstracts accepted, and as of last week, when I last checked the spreadsheet, we have 18 papers published, and a number of others in revision, so that have been that are likely to be part of this special issue in the near future. You can see the geographic spread of these on the map on this slide. So again, focused on the Atlantic, largely on the Atlantic, the Southern Ocean, and the Mediterranean, but with a number of other papers in the Indian Ocean and marginal basins of the West Pacific. And I'm probably missing, I should say, in case you're in the audience and you haven't seen your name here and you've got a paper version, then my apologies for that. That's my oversight. I've grouped these in a number of themes. So those extend from integrated oceanographic modeling, so integrating direct in situ observations or models and geology and geophysics, Pleistocene to modern systems, paleocirculation, so being back beyond the Pleistocene, geohazards and hybrid systems. And of course, many of these papers address multiple themes. And then of course, we have a couple of review papers that are still in preparation at this point. So just to quickly give you a flavor of these themes, I've just put in like a single little box with a single figure or a couple of figures for each of these papers, just to show, to give you a flavor of this. So the two at the bottom here, you've already heard nicely presented by Elda and Henriette. So these are on the Mozambique Channel and offshore Argentina, respectively, or Uruguay, Argentina. We have a couple of other papers that also have a kind of similar approach. So this paper here by Michaela Robesco et al., looking at numerical models, but also again direct measurements from a number of locations in the Malta Escarpment. And these are used there to explain the presence of these large sediment waves that aren't linked or seem not to be linked to turbidity currents in this region. Also a really interesting paper by Pors et al., looking at density-driven bottom currents, so episodic density-driven currents into the Baltic Sea. and these are explicitly modeled as well as the velocities of, so the velocities are modeled, measured, and then the sediments are also mapped and measured in the Baltic Sea. So nice linkage between numerical models and sedimentation. We've got a number of papers looking at Pleistocene to Holocene oceanographic processes extending from individual fjords, in this case from Wills et al. In southern Patagonia, to a number of a couple of papers actually. One on the slide on high resolution seismic stratigraphy and multiple proxies used to reconstruct bottom current conditions in the Scotia Sea. And then we've got a couple of papers similarly in the Mediterranean looking at, again, multiple proxies, describing different modes of circulation, and also that millennial scale cyclicity that Dorrik mentioned in his last slide, his last presentation, sorry. We've got a couple of papers that also look more specifically at currents that are highly erosive, so reconstructing these very erosive currents, some of the bed forms produced by these currents, in this example below from Masola et al., and the impact of cascading water masses and surface currents on the Erik Drift in Greenland. We've got a number of papers looking at ocean gateways, so long-term paleocirculation in the Atlantic circumpolar current and its various water masses. In this paper by Nyajar Farazendi et al. My apologies if I've got your name wrong. And also this on large buried drifts offshore Uruguay by Kirby et al. And then we've got another interesting paper by Lynn et al. Looking at ancient gateways in the kind of paleo-Mediterranean tideflow water offshore West Africa, actually. So we've got a number of papers on geohazards. One very explicitly focused on evaluating whether the Contourite drifts offshore southern Spain are more prone to, or particularly prone to failure. In this case, there are specific probably oceanographic effects, particularly consolidation by internal tides and so on, that make these less susceptible to failure. So quite an interesting contrast to some other systems. And then we've got a paper by Gauchery et al. Looking at what specifically geographic conditions, and particularly enhanced erosion by bottom currents, cause slope failure. And then we've got another example here from the Scotia Sea, looking at the interaction of Contourites and mass wasting. Hybrid systems, we've only got one paper on hybrid systems, well, as I've categorized them at least, but we do have another couple that are in revision. But there's this nice paper by Pudahena et al. Looking at large-scale sediment waves again in the Congo Fan, and reconstructing paleocirculation from these sediment waves. So that is just intended to be a flavor of what we have already published, especially. So we've got another number of people together, and these will eventually be collated into a virtual special issue. So we don't have a physical hard copy of this special issue, but this will be coming soon to a screen near you. So keep an eye out for this.
Coming to a screen near you, I like that. And I hope that many of the papers, the authors of these papers, will be able to make it to Edinburgh next September in order to present some of the work at the meeting. That'd be fantastic. Or at one of the other conferences, which I'm now going to invite Javier to introduce a couple of conferences that you should get into your diary that are very relevant.
Give me 1 second.
Yeah, no problem. Sorry, caught you off guard.
No, it will be very brief now, I promise. So, there we go. Yeah, as Rachel said, next year we have other conferences, and one is going to be in May, between the 18th and the 19th of May in Lisbon, about mixed systems. And you can see all the information in the webpage of APG for this workshop. And in parallel to the conference, we are offering a field trip, pre-conference field trip, to see the water deposits close to Lisbon in the Jurassic. And the deadline for submitting abstract is on the 20th of December. And the second conference is going to be by the end of November next year about oceanic gateway. This was a conference that we planned to organize 2 years ago, that we couldn't do because the COVID situation. So it's planning by the end of November about oceanic gateways. So it's going to be 3 days conference in London. And that's all, Rachel. Thank you.
Super, thank you, Javier, and hope to see yourself and many other people who are at this meeting at those conferences as well. So with that, we're going to move next on to the formal discussion or open forum, where we're going to address a couple of the questions that we didn't get to address during the technical program. So I'm going to sign out and hand over to Dorrik to chair the open forum. Thank you. Yeah, thanks again to all our speakers today. It's been absolutely fantastic.